This is the video for Chapter 10 about doing hypothesis tests with two populations. There are only two sections that we're going to talk about in this chapter, and that is Section 10.2, which is inferences about the difference between two population means, and 10.4, which is inferences about two population proportions. First, let's talk about two means. What we'll do is use sample data from two independent samples to test a claim made about the difference between the two population means. In all of these problems, since we have two populations, we'll have to use subscripts to tell the difference between the two. So here our two population means are mu1 and mu2. And we'll assume that our population standard deviations, which would be sigma 1 and sigma 2, are unknown. So we won't have any information about the population standard deviations. Here's the notation for this. Mu1 is the population mean. N1 is the sample size for the first sample. X1 bar is the sample mean for the first sample, and S1 is the sample standard deviation for the first sample. We'll have all the same notations for the second population and second sample. They'll just have 2's instead of 1's as subscripts. So the requirements for this type of test are that our population standard deviations are unknown. No assumption is made about the equality of the two population standard deviations. The two samples have to be independent, which means that they're selected separately. Both samples are simple random samples, and either or both of these conditions are satisfied. Either the two sample sizes are both large, so both sample sizes are bigger than 30, or that both samples come from populations having normal distributions. If we have either one of these two or both, then we're okay. Now, when we're doing these hypothesis tests in this class, we're going to assume that for our null hypothesis, we have mu1 minus mu2 is equal to 0. That makes our test statistic formula a little bit easier. So here's the test statistic formula that we're going to use. And this, you'll see it's just a little bit different than the one that's in your textbook. The only difference is that the one in the textbook has something else subtracted here in the numerator. We don't have to do that because we're assuming that mu1 minus mu2 is equal to 0. So here's the test statistic we're going to use. Notice that the letter over here on the left side is t. That means we're going to be using the t distribution for these tests. So here's an example. In this one, a headline in USA Today proclaimed that men and women are equal talkers. It referred to a study of the number of words that samples of men and women spoke in a day. In the table below here, we have the results from the study, and we're going to use a 0.05 significance level to test the claim that men and women speak the same mean number of words in a day. And then we'll answer the question, does there appear to be a difference? So here's our sample data. And again, our two samples were selected independently. So we had one sample of men. The sample size for that was 186. And we have the sample mean and the sample standard deviation for how many words they spoke in a day. And the second sample was women. There were 210 subjects in that sample, and here's the mean and the standard deviation for that sample. So our requirements to do this type of test are all met. We don't know anything about our population standard deviations. We're assuming that they're not equal. We have two independent samples. Both of them we're assuming are simple random samples, and both samples are larger than 30. So now let's think about what our hypotheses need to be. If we go back to the claim that we're testing, the claim is actually that men and women speak the same mean number of words in a day. So if we think about that, that would be saying that mu1 is equal to mu2, so that they're the same. And notice that if we subtract the mu2 from both sides, we get mu1 minus mu2 is equal to 0. Now the opposite of that, if we're thinking about the opposite of this equality, would be that mu1 minus mu2 is not equal to 0. Now since this doesn't have an equal, this is going to have to be our alternative hypothesis. And since the one up here has a 0, this would be our null hypothesis. So that means that we're going to have our null hypothesis being mu1 minus mu2 equals 0. And again, this is always going to be our null hypothesis in these types of problems. The only thing that's going to be different is our alternative hypothesis. And in this case, that's going to have a not equal to. To go on with our hypothesis test, we know the significance level we're using is 0.05. And to find our test statistic, this is the formula that we're using, and we just have to go back and plug in these 6 values from that table and calculate it out. So here was the sample mean for the men, the sample mean for the women, sample standard deviation for the men, the sample standard deviation for the women, and our 2 sample sizes. And remember, when you're doing this, that in the formula it's S1 squared and S2 squared. So don't forget to square those 2 numbers when you're working this out. Also, the 2 sample sizes are both underneath the square root. So don't forget that part either. If you work this out on your calculator, you should get something like this, negative 0.676. And notice that it definitely should come out to be negative because when we're subtracting here, our first sample mean is smaller than our second one. That gives us a negative number in the numerator. So we should definitely get a negative test statistic. Now here's something that it doesn't talk about in your book whatsoever. In the book, it gives a fairly complicated formula to figure out the degrees of freedom in a problem like this. For this example, we're just going to use the smaller of N1 and N2. Or N minus 1 and N2 minus 1. And that's how we're going to get our degrees of freedom. This is actually a little bit more conservative than using the formula in the book. And since in the problems, you'll either be given the degrees of freedom or you'll be using something like StatCrunch to find them, we really don't need to use that complicated formula. So if there does happen to be a place where you need to figure out the degrees of freedom on your own, you can use this method. You can just take the smaller of the 2 sample sizes and subtract 1. So that's what we're doing here. And we're using the area in 2 tails in our table because this was a not equal to in our alternative hypothesis. That means it's a 2-tailed test. So if you look in the table, if you look at 185 degrees of freedom, that's not even in your table, but the closest value is 1.972. So our 2 critical values, since we have a 2-tailed test, are plus and minus 1.972. So here's what we've got. Here are 2 critical values. And remember, your t-distribution looks very much like the normal distribution. And then if we plot our test statistic, the negative 0.676 would be somewhere in here. Well, it's not in either of the 2 tails, which means it's in the region where our conclusion would be fail to reject. Now let's look at what would happen if we did this problem with StatCrunch. In order to do this, we would have to use the 2 sample t-statistics with summary because all we have is summary data. So we've got the sample mean, sample standard deviation, and sample size for each of our 2 samples. So we would pull this up and just input our information here. And you do want to uncheck the pool variances box because we're not using pooled variances. Then you would go on to the next box and select hypothesis test. The difference between our means for our null hypothesis is 0, and then we were using a not equal to for our alternative hypothesis. So then if you click on calculate, here's what you're going to get. And notice the degrees of freedom that StatCrunch comes up with. This would be similar to what you would get using that formula in the book. So here's the t-statistic that it calculated, and that's the same that we got, negative 0.676, rounded to 3 decimal places. And the p-value that it came up with was 0.4998. So here the p-value is much bigger than 0.05. And that again would tell us that we would be failing to reject our null hypothesis. So for our initial conclusion, either way we do this, with critical values or with p-values, we fail to reject the null hypothesis. Now in this one, since our claim was actually connected with our null hypothesis, our final conclusion is going to be worded a little bit differently. Because if we fail to reject the null hypothesis, that means that we don't have enough evidence to reject the claim. Because our claim in the first place was that men and women speak the same number of words in a day. So by failing to reject this, that means that we have enough evidence to support this. So here's one way you could word your final conclusion: that there's not sufficient evidence to warrant rejection of our claim. And there was a question that went along with this too, and this answers that. There does not appear to be a significant difference between the two means. Now let's talk about testing for 2 population proportions. Again, we're going to use sample data from 2 independent samples. We'll be testing a claim made about the difference between 2 population proportions. And again, we've got 2 different populations, 2 different samples, so we'll use the subscripts to let us know which one we're talking about. The requirements for this type of test, again, we have to have 2 independent simple random samples. For this one, for each one of the 2 samples, the number of successes has to be at least 5, and the number of failures has to be at least 5. And here's our notation. We've got P1 that stands for the population proportion for the first sample. N1 is the sample size for sample 1. X1 is the number of successes in the first sample. And P1 with a bar is the sample proportion for the first sample. Now the other thing we have to calculate for proportions is the pooled sample proportion. And we say pooled because this means we're taking the 2 samples, putting them together, and putting the number of successes together. So we're getting a proportion over both of the samples. So in order to do that, we just on the top add the number of successes, and on the bottom we add the sample sizes, and then we divide. And again, when we're doing these tests, we're assuming that the difference between the 2 proportions is 0. So that gives us this formula for our test statistic. And notice over here that we have a z, and that means that we'll be using normal CDF on the calculator, or we'll be using the z-scores tables for critical values. And notice the different notations in here. This is one of our sample proportions. So this is sample proportion from sample 1. This is the sample proportion from sample 2. And down here, where we have the p-bar with no subscript, this is our pooled sample proportion. So here's an example. In this one, we have results from car crashes. We have fatalities, whether or not there was an airbag available. So where there was an airbag available, there were only 41 fatalities out of this many total crashes, or this many total occupants, I should say. And in this one, where there was no airbag, there were this many fatalities out of this many total occupants. So if we want to compare the proportions of fatalities for those in cars with airbags to the proportion for those with no airbags, we'd have to look at this as two different populations. So our first population would be those with an airbag available. So P1, which is our population proportion, would be the population proportion of fatalities for those in a car with an airbag. And population 2 would be those with no airbag. So our P sub 2 would be the population proportion of fatalities for those with no airbag. So we're going to use our sample data and a 0.05 significance level to test the claim that the fatality rate of occupants is lower for those in cars equipped with airbags. So first, our requirements. Remember, we have to have two independent simple random samples. We're going to assume that we have those. And our number of successes and number of failures for each has to be at least 5, and we have that. So now we can go on to our hypotheses. Now, if we're looking up here, we're testing the claim that the fatality rate for occupants is lower for those in cars equipped with airbags. And the ones with airbags, this was our first population. So this is going to go with sample number 1, population number 1. So, and remember, when we're doing our hypotheses, we're comparing our population proportions. So we're looking at P1 and P2, and we want to compare those two. So if the fatality rate is lower for the first population, that would mean that we would have P1 less than P2. Now, since this is an inequality, it doesn't have an equals, that is going to have to go with our alternative hypothesis. And to make this easy, again, we're always going to assume in these kind of problems that we have P1 minus P2 equal to 0 for a null hypothesis. This would be the same as saying that P1 is equal to P2. So for our alternative hypothesis then, if we take our inequality up here and subtract P2 from both sides, we would have P1 minus P2 is less than 0. Our significance level is 0.05, and for our test statistic, we need our pooled estimate, or our pooled sample proportion, to use in our test statistic formula. So we're going to calculate that first. This was the formula, so we're taking our two numbers of successes, which were 41 and 52, and then our two sample sizes on the bottom. And if we add and then divide those two results, this is what we get for our pooled sample proportion. And then here's our formula for our test statistic. So the pooled sample proportion is going to go here and here. And these two are our actual sample proportions for the two different samples. So where all the numbers would go in here, our first sample proportion would be 41 over 11,541. Oops, our second one, that's supposed to be a minus there. Our second one would be 52 over 9,853. And then here we have our pooled sample proportion times 1 minus that. And then in parentheses we have 1 over our first sample size plus 1 over our second sample size. So if you work all this out, and do be careful with the rounding, don't round, especially in the cases of these sample proportions. Take them out, as we did here, take them out to at least 6 decimal places. Otherwise, you're going to end up with rounding error. And do all of these operations underneath the square root first before you take the square root. So if you work through all that on your calculator, you should come up with a test statistic of approximately negative 1.91. And here's our picture, and remember that our alternative hypothesis was that P1 minus P2 is less than 0. That means this is a left-tailed test. Which means that we've got our test statistic here, and we're going from there to the left when we're talking about our p-value. So if you wanted to find the p-value on your calculator, you would do normal CDF. And since we're going from here to the left, we want to go all the way out here for our lower bound, so we want to make it something like negative 10, and negative 1.91, and 0 and 1. And that should give us 0.0281. Now if we were doing this with our table, then we would just look up negative 1.91 in the table, and since this is going to the left, that's what the table gives us anyway, and from the table you also get 0.0281. Here's how we would do this in StatCrunch. Since we're doing a test about proportions, we'd select proportion to sample with summary, and then we just put in our number of successes and our sample size for each one. Then we would select hypothesis test. Our null hypothesis is going to have a 0 here, and our alternative hypothesis has a less than. And then here are our results. Notice they give us the sample difference, which is the difference between the two sample proportions. Standard error, the test statistic is again negative 1.91, and the p-value is 0.028. So since we had a significance level of 0.05 and our p-value is 0.0281, that means that our p-value is smaller, and that means our initial conclusion is that we reject the null hypothesis. Now for the final conclusion, the original claim was that there were fewer accident fatalities for occupants in cars with airbags, and that was our alternative hypothesis. So what this means is that there is sufficient evidence to support this claim. So based on these results, it appears that airbags are effective in saving lives.